All right, so hello and welcome. Howdy. We have another LeetCode question to look at today. I don't really know what to do with myself right now. I'm kind of all over the place. Figured I'd just solve some more LeetCode problems. It took me quite a while to get going today. I had a few things I wanted to take a look at before I started. So yeah, I've seen this question before. I've thought about it before. It's not a new question, but I think it's a relatively easy question. As far as like hard questions go. So we'll look at it. Um, we'll see how I do. I might be eating those words shortly. Yeah, 49.5% is pretty high. What was the last one we did? 30, yeah. Lower the percentage, the harder the question typically. This is probably more on a medium level of difficulty than a hard, but that's okay. The median is the middle value in an ordered integer list. If the size of the list is even, there is no middle value, and the median is the mean of the two middle values. For example, 2, 3, 4, median is 3, 2, 3, median is 2 plus 2 divided by 2 plus 3 divided by 2 is 2.5. Implement the median finder class. Median finder initializes the median finder object. Void add num adds the integer num from the data stream to the data structure. Find median returns the median of all elements so far. Answers within 10 to the negative fifth, the actual answer will be accepted. So we're going to do some, arithmetic. What do they call that? Some floating point arithmetic. And yeah, there's some on I forget where it is. There's some oh, okay. Oh, I didn't mean to comparison. That's what I'm looking for. There is something on CPP. Epsilon, that's the one. Yeah, this should be like, I should probably favorite this. There's an explanation here about almost equal on epsilon. I'm going to save this. Give me 1 second here. I'm going to save this page. Yeah. Yeah, we'll save it directly to our bar. That's fine. Yeah, so this is useful because they have a explanation. Not only do they have an explanation, but they have some code here about using the machine epsilon to set your bounds on your comparisons. You can also use fixed point literals. Is there fixed point literals in C++? I mean, you could write your own if you wanted to. Yeah, you can make your own class. How old is this? Oh wait, 13 years ago. Whew. What's the highest? Nobody got an upvote. Nobody got a check mark on the answer. No, this answer is no good. Okay. This question doesn't get nobody wins in this question. No winners. No performance penalty for using simple and lean abstractions, just concrete classes. Precisely the place where using a properly engineered class will save you a lot of bugs. Yeah. Probably a good fixed point class somewhere on the internet. Start looking at boost libraries. Try mine. I wrote one. Here you go. Yeah, interesting. Yeah, that's what I would do, man. I think fixed point is better because floating point you have to deal with like potentially getting things wrong. That's a good interview question for like what do they call it? Firms that are dealing with like trading systems and things like that. You could tell them, could write my own fixed point class if I wanted to. Anyway, I'm pretty sure I already know what I'm gonna do for this question, by the way. Median of all elements so far. Answers here. Median, add num, find median, add num. Yeah, so I think the easiest way to do this is just to use a. You probably want to use like a multi-set for this. It's probably better to do it that way. The tricky thing with multi-sets is, no, actually, this should be fine. That actually works. Yeah, you're gonna use a multi-set you're going to add numbers and remove numbers from the set, and then you can use it'll keep it ordered, and then so you could do this in logarithmic time. You could add numbers in logarithmic time, and you could find the median in logarithmic time. You could just use a pointer in the multiset to the middle if it's odd, and then the center if it's odd, and the two centers if it's even, and that's it in terms of the size. I think one element of the data structure before calling find median. At most 50,000 calls will be made. All integer numbers are in this range. How would you optimize your solution if 99% of all integer numbers from the stream are in the range? How would you optimize your solution? Oh, that's interesting. Well, if they're in the range from 0 to 100, you can use a sort that's a little bit more efficient. Like you can actually use a frequency map, I think, instead to find the median relatively easily. So it wouldn't be logarithmic time anymore, it'd be constant time with respect to 100, I guess. There's like a few different ways, I guess you could do this. And then if most integers are in this range and there's only a couple that are not, only a few, then I guess you could still use a frequency map to find the median. These are good questions. I don't know how exactly I would do that. I'll probably read the discussion, find out what the recommendations are. I mean, this is a general approach, right? To use a multi-set. But I guess a frequency map would work here. I'm not even sure. And then I guess a modified frequency map for this one. Yeah, you can do a just a loop through 0 to 100 to count how many numbers you have in each slot and figure out whether or not you're past the median or not. Right, so this is like if lots and lots of duplicates. Technically, it would be constant because you don't have to go through 100 slots, so it's constant time solution. I mean, it's maybe not the fastest it could be because a logarithmic solution might be even faster, and you have to have a lot of numbers to be. It actually wouldn't be faster because in order for, if you take 100, in order for log of 2 of x to be equal to 100, that means you need to have more than that many numbers that you're working with. So it's actually like never more efficient. How would you, I don't know. I guess you could try to keep track of a moving median kind of deal. So if you add a number, because we're not removing numbers, we're only adding numbers. So I guess you could kind of optimize things slightly there too. But you would, like, I guess you'd have like a running total of like where your median is, and if the number is smaller than the median, then you potentially move to the next number for your median or your two medians, and then if the number you added is larger, then potentially move to the other side. Something like that. And yeah, you can kind of keep things in a. You can use counting sort to keep everything in one frequency map in order to figure out like what the next number would be. You can do it that way instead of keeping like a multi-set. But here, this is interesting because I don't know if 99% of the integers are in that range. How would you optimize the solution? That's an interesting question. Can maybe use a linked list instead of an array, and in that way you can still move through the linked list, a doubly linked list, so you can go to the left or forward. You still have to sort everything though. So you can use radix sort instead of counting sort. Radix sort's a little more efficient on the larger numbers. As long as the integer numbers are like relatively, yeah, I mean they're between, 100,000. Actually, all of this would be more optimized. Potentially, you could do this in, I guess, constant time with a radix sort. So you could figure out where to place in the linked list using radix sort. Does that work? We're never removing numbers, so I guess the you do need to figure out. No, well you can't add a new number easily inserting the number. Counting sort works nicely for 0 to 100. That's fine. That you should be able to do it all in constant time, and not doing what I was suggesting before, like the stepwise. That actually isn't the way you want to do it. You want to do it by, if the number is smaller, if the number is larger, then you can move to the next spot. You can update your median, and also because it's a frequency map, you can just add the number to the frequency of that amount, and you're fine. So that's you could actually do the same thing for negative 100,000 to 100,000 also, and it's a lot of extra memory, but you can still do that if you wanted to. Radix sort would be the next idea to keep it kind of optimized. It's very similar to counting sort. Instead of a frequency map, though, you'd have something else, I suppose. The tricky thing, though, is the insertion wouldn't be linear constant time. I'm actually not sure if you have 99%, what you would do. You can sort it quickly, but inserting a number into a radix sorted list is not as easy as it is for the frequency map. Frequency map is constant time to insert, but a I need to think about that for a minute. But yeah, we can go ahead and just code this up. So we're gonna have a multi-set, which is just set. We're gonna have I think we just use ints, and we'll just call this multi-set ms, and we'll say ms is a new multi-set, and we add the number and find median. This is as simple as constant n is ms.size and modulo 2. I actually like to do, and 1 is 1, and otherwise, so even or odd, odd, even. In the odd case, you can return ms dot it's actually the other way around. It's ms begin plus n over 2. It's odd. Yeah, if it was 3, so 0, 1, 2, divide 3 by 2, you get 1. 0, 1, so it's actually going to be plus 1 divided by 2. So we shift the beginning iterator over n plus 1 over 2. If it's even, we're going to take const double left center and the right center. Could do something like this also. So maybe this is better. just so that we have double left, double right. So we can do, just call it x divided by 2. Something like this. It's like ms begin plus x, and then ms begin plus x plus 1, right? So it's going to be left, right, and we just take left plus right divided by 2. Yeah. So this is integer division, and then these are doubles. So part of the deal, if you have 4 numbers, 0, 1, 2, 3, 4, you want to add 2. Well, you only really add 1, right, with 4. So 4 minus 1 divided by 2. And you add 1 and then you add 1 again. And then on the other side, I think you actually do want 0. You only want to add 1 of these. So actually, I think it's n minus 1 divided by 2 also. Something like this. I don't know. What does this do? Does this compile? Binary expression. Oh, you know what you got it. I remember now. Yes, this is interesting. So need to advance the pointer. Yeah, that's what you do. That's an interesting, yeah. It's kind of an unusual thing, but we're making heavy use of the SDL here. That's what we're doing. That's what we want to do. And we have pointer 1, do pointer L. I don't know. Advance pointer 1 by x. Advance pointer 2 by x plus 1. And this is just pointer 1, pointer 2. You actually don't really need to do it this way, but, well, yeah, with multi-sets you can't, certain iterator types you can't just add a number, you have to advance the pointer. So we could do both of these. You could actually do, you could do it this way too. It's actually easier, it's more efficient. I should do it this way. So pointer, const, double left, pointer, and now advance the pointer 1 more. And that's pointer again. That gives you the right side and the left side. Something like this ought to work. There we go. Now, one question is, and let's some test cases. They only give us 1. All right. Kind of want to test this a few times before we're done. So there's one more issue here, which is the left, right. This actually, if you only want to look at this if it's odd. Even you could have the problem with this is even could be if it's empty, right? we just want to say it's greater than 0. Can't be even and 0. That's the only tricky thing here. All right, so let's try one more test here. Add num. So let's do find median. Add num. Add num. Find median. And I just want to like find the median, add the number, find the median. Just do that over and over a few times. One, two, three, four, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Find the median of empty. Add number 1, find the median again. Add number 2, find the median again. Add number 3, find the median again. Add number, I don't know, 500. Let's see, what do we get? Invalid test case. Oh, okay. We don't have to handle this case then. That's fine. All right, fair enough. Nice. That's always good. Let's see how we do it on time. Yeah, I do want to ponder a little bit more. Oh, this one too. Okay. Well, actually, this is just a copy of the other one then. And these are the same. There is, yeah, I don't know. I have to think about this follow-up a little bit. 1.5. All right. I guess we just go for it. I don't know. Yeah, probably just go for it. There's very likely something I missed. I'm nervous. Oh, oof, really? What? Wait, what? Oh, wait a second. No. What? Did I do that wrong? Uh-oh. There's always something I missed, man. Linear. Oh no. No. I thought it's logarithmic. No. Oh, that's awkward. Oh. No. Oh, that's very awkward. Whoops. Oh. Okay. Well, that's a mistake. Ouch. Uh-oh. Uh-oh. Ouch. That's not good. I thought it was I thought it was that easy. It was not that easy. Oof. Oof. Uh-oh. Uh-oh. Mistakes were made. Mistakes were made. Uh-oh. Ouch. Ouch. Can't actually do what I thought I was going to do. I thought I wanted to do. Oh no. Oh no. Uh-oh. 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 Now I think it's okay. I think we're not in too much trouble here. But it's not good. Not ideal. Not ideal. What's previous and next? What are these? These are potentially linear. Also linear. Oh boy. I don't think that we can use this the way I'd like to. Uh-oh. Uh-oh. Hmm. Some words will not come out sorted. Come not out some sortable words. Huh. Advance the count. Oh, I see. Count elements have equivalent keys. Oh boy. Uh-oh. Uh-oh. Hey, it looks like I can't do this the way I would like to. No. No. Uh-oh. Uh-oh. Excuse me. So I'm wondering if my question is, Thought I could, can't even do. There's another thing we can do here, which will work. Hi, why, hmm. Uh, okay. So this is the thing that's really awkward, right? You should be able to find, if you have a sorted list, you could find the middle of it very easily. Constant time, right? It's just the middle element. However, with a sorted set, they're special because they're not lists, they're actually trees. But you can still find the middle element relatively easily in a tree. Especially a sorted tree actually would be the... If you had kept it in an actual tree, it really would just be the middle element, I think. The head should be every time. It's balanced tree. Well, not always be. It wouldn't always be the head. That's not necessarily true. But certainly you can get in logarithmic time, or a type balanced tree. In logarithmic time, you can find any index for any value. But why? So why do I? Why did I get? What am I missing here? I want the index. Why can't you search by index? Huh. That's really weird. Did it not support index searching? It should. I mean, it's not hard. It's not like you can't. There should be a way to do that. I used to think you just increment the iterator, but apparently the iterator, if you increment it, it actually goes only one by one. That's strange. Why is this not how I remember it? I think you need to find... Huh. Fat key, light key. Oh. Oh. Huh. Well, that's interesting. Wow. Oh man. I gotta sit down and think about this for a while. Wow. Huh. I don't know what I was expecting. Really? No kidding. It's the first time I've been like disappointed by or I misremembered. Well, misremembered, ended up being disappointed by the STL. I thought you could just move the iterator. Yeah, move the iterator to the spot that you want to check, you want to find. If you had a sorted list, you can very easily do what I'm describing here, where you can. Maybe I should just write a. I think that's what I was going to do for another problem, is write a data structure where you can. It's a height balanced tree, but you can also determine very quickly the index of the tree, the indices of the tree. So, if you wanted to find any particular order statistic, you could do that in logarithmic time. Yeah. Well, that's interesting. Huh. I think you could do it in constant time if this was in an array. Although I don't think you can. I think that might be a little bit more challenging to try to have a height balanced tree that also you can find the order statistic lookups in constant time. Excuse me, that might be a little bit difficult, but definitely could do it in logarithmic time, certainly. Just each node just needs to know how many children it has. So I guess I stand corrected. This is not as easy as I thought. It's still not that hard, I think. I think you can just iterate. The iterators that you're working with, you just increment or decrement from the median point. So each time you add a number, you only move there's sort of a base iterator that you move, and you would say, you would copy it and move that one to get the center that's on the right side, but each time you add a new element, you either shift the center to the left or to the right, depending on the size of the value that you've added or removed. So I'm a little bit disappointed. I'm very disappointed, actually. I thought this was like in the bag. I was not expecting to be TLE'd. Okay. Excuse me. No, I know. No, I know. So you have an iterator, standard multi-set int iterator. Call that med. And we're going to insert a number. Say if ms is empty. Then, or actually, so if we were empty, then we're going to say med equals num.begin. Not num, ms.begin. First element, and then we'll say otherwise we have const int val is going to be evaluate med. If num is less than val, else. If so the number that we just added is less than the value, then we're going to standard advance med backwards, and otherwise we're going to advance the median forward. So if we add this value to the right, then we want to move our median up. Add the value to the left, we want to move the median down. Now the tricky thing here is depends on whether we're even or odd. So if we add one value, so if one value, we add another one to the right, we don't move. We're gonna keep our median on the left side. If we add another value, so two values, next value added, if it's to the left, we don't change. If it's to the right, then we move to the right. So it depends on whether or not we are odd or even. If we're even, we don't do anything. If we're odd, so if ms.size only if it's odd, do we do anything at all? And I think in that case it depends on what the two previous. So if both values that we just added are to the right, then actually that's really tricky. I guess it depends. Now we have a whole bunch of different things to consider. Oh, that makes things way more complicated. I mean, it's not like we can't handle it, but it's a lot more complicated than it needs to be. Kind of annoying. So these, yeah, we can come back to this. It's similar kind of logic, but that's annoying. Okay, so if the number you add is to the right, you don't do anything, and it's even, right? So we go from odd, we've added a number, now we're even. If we add it to the right, we don't do anything. If we add it to the left and we're even, we do actually want. So we do have a few different scenarios. We can do the following. So if I could say ms.size is odd, and do some things, odd case. This is the even case. So now in the odd case, if you added something to the right, and we want to update med, so if we add something to the left, so if num is less than val. Now here's another question too. If it's equal to the value, what happens to these iterators? That's kind of a tricky question. I think this iterator becomes invalidated too, which is weird, which is awkward. I don't know if this is going to work as nicely as I would like it to. Yeah, I think once you insert something, this pointer, I don't know what happens when you. Oh no. Oh, I think it's gonna get way more complicated than we want it to be. Uh-oh. Uh-oh. No. Okay. Yeah, I don't know. So what happens? All right, let's go look at multi-sets again. So if we insert, what happens if we insert? Oh yeah, it's interesting. We'll give you an iterator to the returned inserted element. Okay. Oh, interesting. No iterators or references are invalidated. Assertion is successful. Pointers and references to the element obtained while it is held in the node handle are invalidated. And pointers and references obtained to that element before it was extracted become valid. Oh. Obtained while it is held in the node handle are invalidated. And point, I'm not sure what that means. Elements into the container, inserts the value if the container has elements with equivalent keys, inserts at the upper bound of that range. Oh, okay, great. So upper bound of the range. All right, got it. So that helps a lot. And there's a node handle. I don't really know what that does. Associative containers are node-based data structures, and their nodes can be extracted as an object of unspecified type known as a node handle. Node handle is a move-only type that owns and provides access to that element. The value type stored in the node and provides non-const access to the key part of the element and the mapped part of the element. If the node handle destructs while holding the node is properly destructed using appropriate allocator. Using the appropriate allocator of the container, the node handle contains a copy of the container's allocator. This is necessary so that the node handle can outlive the container. Oh, interesting. That type of node handle shown here is node handle. It's unspecified, but each container exposes its node handle type as the member node type. Node handles can be used to transfer ownership of an element between two associative containers with the same key, value, and allocator type, ignoring comparison or hash equality, without invoking any copy move operations on the container element. This kind of operation is known as splicing. Transfer between unique and non-unique containers is also permitted. Whoa! A node handle from a standard map can be inserted into a standard multi-map, but not into an unordered map or a standard set. Oh, that's interesting. Oh, okay, unique and non-unique. Okay, I was gonna say, but you can't go into different containers. That would be kind of wild. Node handle may be empty, in which case it holds no element and no allocator. The default constructed move from node handle is empty. In addition, any empty node handle can be produced by a failed call to container and member function extract. Okay, pointers and references to an element that are obtained while it is owned by a node handle are invalidated if the element is successfully inserted into a container. Oh, I see. Gotcha. All map containers whose key type is K and map type is T, the behavior of operations involving node handles. Undefined if a user-defined specialization of standard pair exists for standard pair KT or standard pair const KT. Oh, that's interesting. Oh, I see. So if you redefine pair, then the node handle doesn't make any sense anymore. That's kind of complicated. I don't really know much about node handles. I don't know if I'm going to use them very much. They're kind of weird to me. I think I get it, but I also don't really fully understand. So we don't. So this has to do with node handles. Pointers and references obtained to that element before it was extracted become valid. Not sure I really understand what's going on here, but it has something to do with node handles. So otherwise, our iterators and references are not invalidated. Oh, sweet. So it's not invalidated. That means, great, we can do what we want. All right, that's what I was worried about. I was kind of concerned if things get moved around, what happens to my iterators? All right, great. So if we're equal, that means we're moving it to the right. So if we're less than, it's gonna our median is gonna move to the right. And otherwise, median moves to the left. So median potentially moves left, median. Okay. So yes. So actually, if we're equal also, so if the number we're inserting is smaller than the median, we're potentially moving to the right, the median to the right. If the number we're inserting is larger or equal to the median, we're potentially moving our median to the left. Yeah, there we go. Okay, that's what we want to do. So in the odd case, so we have an odd case, it becomes, so now we were even to odd case, it's even to odd case. So we were even, now we're going to odd, and this is the other case. This is the odd to even case. Okay, I see why this is considered a hard problem. This probably shouldn't be a hard problem, but I get it now. I get why. Also I got it wrong, so there's that. So there's that. That kind of hurts, but it's okay. Kind of stings. All right, even to odd case, the num is less than the value. We're going to add it to the left. If it's greater than or equal to, we're going to add it to the right. So potentially move our median to the right or move the median to the left. So if we were even, then the median does move to the left, we have to actually, we were even, we're now odd, and we added, so we go from 2, we're on the left, center of the left, so actually is in the correct place, right? So that's if it's no op. Here, we're gonna actually, just for illustration purposes, we're gonna keep it here. Keep this if statement. We can make this one if statement, but we'll keep this sort of double branch. Now, if we're going from even to odd and we move to the left, or excuse me, yeah, our median now, oh, it's so confusing. Median pointer potentially moves left. Yeah, that's what's moving. The median itself is actually moved to the right. Update accordingly. Yeah. Now, these other cases are, now if we go odd to even, if we're odd, and the value we add to the left puts us into an even state, we need to move our pointer to the left. So our median pointer potentially moves to the right, shift median to the right, to the left to accommodate. So here we move to the left. Now our median pointer, if the number we're putting in, so we were odd, and now we're going to even, and we put something on the right side, the median pointer potentially moves left, and the median's in the correct place. No op. Okay. That is a little bit complicated. And now we can say finding the median depending on if we're odd or even. So if we're in the odd case, then we can actually just return the median pointer. If we're in the even case, we need to create, we need to do two things. Take our pointer to be a new pointer to be the median. We're going to say const double left is going to be the median. Have a new pointer pointing to the median, advance that pointer once, and then const double right is going to be that pointer, and then ret is going to be left plus right divided by 2.0. something like this. So we're gonna modify where our median is pointing to as we add values. Yeah, we'll do it that way. But this we definitely want to test a little bit more. So we can say, let's do like 100, and then we're gonna say 50, and then we're gonna say 25, and then 10, and we're gonna do quite a few of these, and then you can do 1, 2, 3, 4, 5, 6, and we'll say 1, 2, 3, 4, 5, 6. See if that compiles the test. So you definitely need to do a little bit more testing here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I don't know what I did, but somehow I didn't get it right. Okay. Now what we want to do is add, so not just add things to the right side or the left side, but we want to add, so these are adding things to the left side. We want to mix them up now. We want to add something to the left, add some things to the left, add some things to the right. So 110, 111, 112, 113, 114. We'll take a look at that next. So how are we doing on time? Yeah, a little over an hour, a little under an hour. I already submitted it too, so that's not good. There are like a bunch of tests I should probably run. Let's add 1, 2, 3, 4, 5. Let's add 6 of these. Let's add 6. So we have 1, 2, 3, 4, 5, 6. Let's do that. All right. Now what we want to do is we want to kind of go back and forth. So I don't know what the median is here. 50, 20, 25, 50, 10, 25, 50, 10, 10, 25, 50, 100, 110, 111, 112, 13, 14. Probably the median of this would be like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 elements. The fifth element, 0, 1, 2, 3, 4. So if these were sorted, it would probably be 100, right? So 10, 10, 25, 50, 100. Yeah. And then 1, 2, 3, 4, 5. 1, 2, 3, 4. So it would be between 100, so it would be like 105. So we want to go under 105 and over 105. So 95, 106, 90, 110. 80 and 150. Something like this. Let's see if that works. We might have an issue with our test case. All right, I think we got it. Let's go for it. I'm not gonna try to test the, I'm not gonna try to test like a lot of different test cases. I'm just gonna submit it and try to basically use their test cases. All right, we got it. Okay, great. That was kind of what I should have done first. I thought that advancing the iterators was not linear time. Didn't realize it's going to walk the tree. But you can advance it one spot at a time. That'll be constant for the one advancement that you do. So what we're doing here is actually, this is logarithmic to add the numbers, and then actually it's actually constant time to compute the median. Because what we're doing is we're actually keeping track of the median, as opposed to and updating the median, as opposed to calculating the median directly at each point. So this is actually a little bit more efficient than my original solution. And I have to submit it 9 times now to make sure my score is padded properly. I don't know, to get back to the description here, I don't know what I would do for, oh, that's also interesting. I didn't think about that. Well, no, probably better to keep track. I was gonna say maybe I'm looking at the amount of memory stored each time, and I'm using, quite a bit of extra memory. It looks like. Apparently you don't actually need to keep this multi-set. I don't know about that, because you kind of need to keep in memory somewhere like what the previous values were. In other words, if you just get like a whole bunch of elements to the right side, I guess, or like let's say you get a whole bunch of numbers, and then you get a whole lot of numbers on the left side. I want to say it's possible to, no matter whatever number you have that you've seen, it's possible to add enough numbers to your set of numbers such that the numbers you've already seen, you need to keep them in memory somewhere because you have to refer back to them potentially. Yeah, I want to say that's the case. I think so. A median is not the same thing as like an average. Hey, we did the sliding window median. Yeah, we did that. Yeah, because you can kind of always add elements to the left side, and that would shift the median down to it would actually shift it further down the left side. Yeah, I don't know, man. I don't know how to optimize the memory on this, quite frankly. I don't really know. I wouldn't know that. I want to say, oh, you know what? Oh, I see. I see. Yeah. So you can, well, no, it's still a lot of memory. I don't know, man. Maybe I should read the discussion here. Well, certainly this one you can optimize quite a bit. Instead of using a multi-set, you can use the frequency map. Yeah. I don't know if you could use a frequency map. Like instead of a multi-set, use a map itself and make that a frequency map as well. That might be less memory. And then calculating your median would be similar, where you would have an index and a key, I guess. Oh, you know what you could also do? I didn't think about this. Well, no, you kind of do want, yeah, you have an index and a key, like a value for the median. So the previous median value, and then like which index in the frequency it is. And then adding and subtracting would be a similar thing here, but instead of updating the pointer, you would just update the index or get the next key, which I think you could do that in a map. So maybe a frequency map would work too in Stutzig at logarithmic time. For adding numbers would be logarithmic time, and finding the median should be constant time. No, that would be logarithmic. So actually would be a little bit slower. I don't know, man. Feels like this should be a little bit faster too. I don't know why. I don't know. I think I have to go look at the discussion to find out. But oh whoa, 1, 2, 3. How many do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh yeah, I'm just hitting this every 6 seconds. I don't know, man. I feel bad. Feel bad getting a low score for all this time and effort in. I get like a 40% success rate. This feels bad. Feels terrible. All right, I think that's probably it for me. Yeah, I don't really know what I would do. Yeah, definitely you could use counting sort here. Maybe there's a way to optimize this slightly that I don't realize. Probably would want to check the discussion to find out. And then 99% of all integers are in this range. How could you optimize? That's really tricky, man. I don't know. Well, actually, yeah. Oh, this is interesting. Okay, check it out. You only need to count if. Oh, this is really clever. Okay, yes. So you can optimize this the same way, the second choice, the same way as the first choice, because you're only looking at the median, right? If you're only looking at the median, it means that the values that are out of this range, you're never going to see them because 99% are in this range. The median is always going to be in this range, so you don't actually need to keep track of those numbers anymore. Ah, check that out. That's interesting. Hey man, hey, how's it going, Devesh? Welcome back. Hello, hello. Welcome. Howdy. So you could really optimize the memory because you don't actually need to keep track of those numbers. You just need to know how many of them are less than 0 and how many of them are greater than 100. And then oh, that's really clever. Yeah, so then you can always adjust your median there. So you can use, so both of these cases, you could use a frequency map between 0 and 100, so that's a lot less memory. It would be constant time to figure out what the new, as you add numbers, to update where the median is. Constant time to update, constant time to add the values of the map. And both of these are almost the same. In this second case, you know the median is never going to fall out of that range. So you actually don't need to know what the numbers are that are larger or smaller. You just need to keep a count of how many are larger and smaller. So both of these would give you constant time and space and be really quite efficient. I don't actually know. There's probably a better way to do this that I don't realize. But I don't know. I'm not sure. I mean, it's constant. It's, yeah, it's constant for the median to give the result, but it's logarithmic. It's actually, yeah, it's logarithmic to add the numbers, and I'm keeping track of every number too in a multi-set. Maybe I can make this a frequency map and slightly optimize it, and then maybe it'll be a little bit more efficient when I search over the keys as well. But I'm not really sure. I don't know. It's kind of questionable. I'm not too sure. So that's my analysis here. How's it going, Devesh? Let me read the problem to you, Devesh, so you have some idea of what's going on here. I got owned by this problem, man. I thought it was gonna be like 5-minute problem, but I made a mistake. So find the median from a data stream. The median is the middle value in an ordered integer list. If the size of the list is even, there is no middle value, and the median is the mean of the two middle values. For example, array 2, 3, 4, the median is 3. Array 2, 3, the median is 2 plus 3 over 2 is 2.5. Implement the median finder class. Median finder initializes the median finder object. Add num int adds the integer num from the data stream to the data structure. Find median returns the median of all elements so far. Answers within 10 to the negative fifth of the actual answer will be accepted. So you have add num, find median, add num, find median. And the constraints at most 5 times 10 to the fourth, so 50,000 calls will be made to add num and find median. There will be at least one element in the data structure before calling find median, and the numbers themselves are going to be between negative 100,000 to 100,000 inclusive. And then they have some follow-up. Say what would you do differently if all the numbers are between 0 and 100 inclusive? What would you do differently if 99% of those integers are between 0 and 100 inclusive? And so the solution I gave for this one, I said dump all the numbers into a multi-set and also keep a median iterator. So create the multi-set when you initialize, and each time you add the number, you can update depending on where the number is relative to the current median. That'll either move the pointer to the left or to the right, depending if you're odd or even, or if it's larger or smaller. And I went through those different cases here and added no ops just so it's clear what's happening. Oh, we don't need this check anymore. Oh, no, yeah, that's interesting. Yeah, and I also just have a check to initialize the pointer in the first place. And then finding the median itself, if we're odd, we can just take our pointer directly. If we're even, that means we're always going to keep our median on the left center. So we just need a pointer to advance to through our multi-set, which is going to be a sorted list of keys where the keys are not necessarily unique. And so we just get a pointer to the next element in our list. It's not a list; it's actually a red-black tree of elements of nodes. But yeah, so we can find the next largest element to the right of our median, and in theory that should be constant. I think it's constant in this parameter, which is just 1, so it should be constant time to update that. So it'll take constant time to find the median, and it'll take logarithmic time to add our new element to the list, to our set. So that's my solution. And I got this wrong initially though, because I forgot that your medians are not, or multi-sets, you can't advance an iterator through a multi-set in logarithmic time. I tried to just advance 2 iterators to the left center and the right center, or the center. But actually all of those operations are linear, not logarithmic, as it turns out. So it was too slow at TLE'd the first time, and then I updated this. I said, oh, okay, so we'll keep track of the median then between adding numbers and update it that way instead of trying to just. But if you had you could have a data structure. You can conceive of a data structure where you have a sorted set of elements, and you can actually know, like for a given index, basically an order statistic, you could easily find that node for that order statistic. That's not inconceivable. That's not actually that hard to program, as it turns out. It's just you do need to know a little bit about how to implement a height balance tree, and then how you would modify, like if every node has information about the number of children that it has. So when you're swapping things in a height balance tree, then you just need to update that. So it's not that hard to write a height balanced data structure that you could also find the ith order statistic in logarithmic time. It's just that's not an out of the box implementation, out of the box data structure for C++, which I thought multi-sets had that. I thought all the height balance based, like the maps and the multi-sets and the sets and all those things, the multi-maps, all those different data structures, I thought each of those did actually have, because they're height balanced, I thought they did actually have access to the order statistics using at least logarithmic time. By the way, if you had a sorted list, obviously you could find any order statistic in constant time. But when it's a tree, it's a little bit more complicated, I suppose. But you could even conceive of a data structure that you can update. I actually don't know if it's that. I don't know, because I don't know if you could easily dynamically update like an array, for instance, because you'd have to change the order statistic for all the other elements too. Like if it was constant, just basically have an integer that points to one or the other. So it'd be kind of challenging to do that in constant time. But I know you can do it in at least logarithmic time. You can kind of maintain the ith order statistic in logarithmic time for all this order statistics. I think that's actually a question, by the way, on LeetCode here, is like there's an all of log n question, and I think that's probably what they're referring to. But yeah, and the solutions to the follow-ups seem to be you can do instead of using so I could maybe optimize this slightly by using a frequency map instead of a multi-set. So the things would be stored, instead of like every key being stored and having duplicates, it just have a frequency map, so we know how many duplicates there are. And then the logic is probably roughly the same for both parts here, although just using a frequency map instead of a multi-set. And so we don't just advance the iterator forward, don't necessarily advance the iterator forward, and we probably also have a value for the iterator, and also a like the key, and the index, like so how far we are in sort of the frequency map. Like if we have 6 of the same number, how deep are we in there? Are we on the fourth number? Are we on the first number, or what have you? So it's be relatively easy to update. Probably more efficient to update ourselves, and also more efficient to store the information, the data, and then also like because those things are more efficient, there's less data, so the logarithmic factor is smaller. Something like that. That's kind of what I'm thinking. I'm thinking that the more optimal solutions did something like this. And then you can use a more direct frequency map. You can actually use just a single array of 100 elements if you wanted to for the or 100 indices for the all the numbers were in the range from 0 to 100, and that's a lot easier also to figure out what the median. It would be the same kind of algorithm that I was just describing with a more generalized frequency map, but this would be just constant time instead of it'd be constant time all around instead of logarithmic insertions, because you're inserting directly into a frequency map with a like a 1-to-1 between the key and the index. There's no hashing or anything. You could use a hash set here too if you wanted to. You could also use, oh no, excuse me, you don't want to use a hash set here. I'm sorry. The reason why you don't want to use a hash set here is because it's hard. It would be impossible or very difficult because there's no ordering on a hash set, implicit ordering. So you wouldn't know ordering on the keys, so you wouldn't know how to update the median properly. However, you can use the same algorithm I was just describing to update where your median is. And then here, this is the same deal, except now you just have 2 extra numbers to keep track of how many things are less than 0, how many things are larger than 100. You don't actually care to keep track of any of those keys, because if 99% are between 0 and 100, it means you're never gonna, the median, it's impossible for the median to ever be outside of this range. So you don't really care about what those other keys are. You just care that they're larger or smaller than 100, smaller than a 0 and larger than 100, and how many of them there are to figure out how far off you've got to move your median. That was a mouthful, but yeah, that's the follow-up frequency map for both of these, using something like a counting sort to figure out where the median is supposed to be, and update the median constant time, add numbers in constant time, and slightly modified for the second case where you just have to keep track of how many are smaller, how many are larger, but it's just pretty much the same solution as the previous one. And then here you could still use a frequency map, but you'd want to have some ordering, and it's just a slightly more efficient approach than the one that I have here. I think asymptotically it's not more efficient, but I think for like if you're comparing yourself to the other solutions other people have submitted, then it probably would be a 1 or 2 orders of magnitude faster. Good work, thank you. Yeah, I realized I was just rambling for almost 10 minutes after you said hello about how to do this. So thanks. So yeah, that's this question. I didn't really ask you how you are. Hope you're doing well. I'm actually going to probably start another problem. I'm gonna, what do you call it? Probably end this stream. So this video is sort of, I mean, it's an hour and 20 minutes already, but so the stream is somewhat self-contained, and then start another problem. But yeah, as you can tell, I think I messaged you a while back. I was like, yeah, if you want to get prepared for interviews, you could just, grind LeetCode. Grinding LeetCode is kind of rough, I have to say. I've been doing okay, but like, I don't know, it's challenging. It's really challenging. Some of these questions are really hard, but I've made pretty good progress. So yeah, I'm way behind on the hard problems though. I've gone through like maybe 50 or so now, and I've got like 400 to do. I want to get to, what's going to happen is I'm going to get through about 200 of the hard problems, and then after that I'll start seeing like more than just the hard problems. I'll start seeing the easy and the mediums, because I've done like half of the easies, a third of the mediums, and like a fraction of the hards. So once I get them all up to a half, like I'm just going to go through all the problems straight through. Once I get to about a half on everything, then I'm going to start to get a mix of easy, medium, and hard. And I'm getting to a point where like some of the hard problems I can solve very quickly. But the ones that I try to solve them quickly, I tend to fail them. I just misunderstand the problem. I just misunderstand something. So yeah, so I wouldn't say I can solve them very quickly, but if I get it right, I guess, if I get it right, I can do it quick. But some of them, I don't know, some of them I can do pretty quick, but some of them not so much. The goal is to be able to solve like trying to be able to solve these problems in like 5 to 10 minutes each, and then if I could do that, then 1,000 problems won't take me that long. Maybe take me like a month or something. Something like that. That's the goal. I don't think I'll ever get there. Like, these are hard. Like, these are challenging. Like, it takes me a while to figure all this stuff out and get through it all. It's challenge, but anyway. But yeah, thank you for watching. I'm gonna be right back. I'm gonna just basically restart the stream on another problem. But yeah, I hope you're doing well. I didn't really ask you very much. I guess, you know, I hope your own, I guess, adventures in software development have been interesting and fulfilling. Feel free to let me know how things have been going. All right, let me start another one.